Yeah, people want to join. Okay. Yeah. Uh, I think what we were doing last time, we were looking at discrete time convolution, and we were looking at ways of dealing with long sequences, on convolving long sequences. And last time we looked at the overlap add method. Uh, and I hope everybody is okay with what we did or has no questions about what we did, what we looked at. I think we managed to get the final sequence. Uh, the steps was, of course, first to divide the sequence into shorter blocks, which must be either equal to in length to the um, impulse response, or um, or longer. They are at least equal in length to the impulse response. But the issue thing would be to try to create, because since they can be longer, is to try to create one which will make it possible, later to make it easy, and also possible to let me see, let's see, wanting to join, yes, possible to use the endpoint DFT matrix, especially the even numbered DFT matrices. And why of course they become useful, the even numbered, is because if you're going to do the if you're going to use the radix 2 FFT, we are going to look at the radix 2 FFT. It means it's important that you are using DFTs, which are multiples of 2. Yeah, that's why sometimes we tend to try to create a sequence that is a factor of 2. Yeah, otherwise you can use even 5-point DFT, you can use 6-point DFT. Well, not even 6-point DFT will not help you much, because if you're using, in the radix 2 FFT, you move from 2 to 4 to 8. So probably I don't know how to put multiples of what, maybe powers of 2. Yeah, if you're using a radix 2, then it's good to use the the length which is a power of 2, which means either you're using 2, 4, 8, 16. Yeah, because then you can be able to use the FFT algorithm. Uh, well, one of the FFT algorithm, which is the radix 2, either, I think we are going to look at that, but it makes sense to use either 4 or 8 or 16 if we are going to use the FFT algorithms. So we did work out. In this case, we just chose equal to the length of the impulse response, and then, of course, added, that's part of the algorithm. You add m minus 1, you add m minus 1 zeros, you pad with m minus 1 zeros, and then so that gives you the length of your new sequences, and then use the circular convolution method. That is the circular convolution method. And once you do the overlap add, actually, you notice we did this and use circular convolution method, but what it ended up giving us is the linear convolution. Yeah, what we ended up with is a linear convolution, and you can check that by simply trying to work out this uh, using the linear convolution method. Yeah, I think it's important to know that we have used the linear convolution method with this with their new sequences. But eventually, what you ended up with is we have used a circular convolution method, but what we ended up with is a linear convolution. Because at the end of the day, it is very exciting, it's good to note that at the end of the day, the output of a system is, the output of a system given a certain input is simply the linear convolution of that input with the impulse response. Yeah. But it's also important to note that when you're working with the circular convolution, when you're working with the convolution theorem, what you're talking about is actually the circular convolution. Yeah, it's actually the circular convolution theorem. Yeah, and not the linear convolution theorem. Yeah, it's a circular convolution. So, in as much as you're trying to look for the output of a system, it's important to know that when you apply that, that gives you circular. So, eventually, what you end up getting, during the steps, you need to subject it to algorithm that will end up giving you the linear convolution. And of course, this is one of them. This one gives us linear convolution, and we can test that. Actually, I decided to create a table here just to counter check our answer with using tabular method. Yeah, we know how the tabular method works. So you have here on one side. I hope you can see my table here. It should be visible. Yeah, you can see my table. Well, silence, I assume you can see my table very clearly. Okay. So, oh, it is visible. Thank you. Yeah. So if we check this using tabular conversion method, so this is we use a very easy H of n, 1, 1, 1. So this is H of n. Go for it. Yeah. H of n. And this is your long sequence, x of n. So this is x of n. It has got 10 samples, 10 real samples. Of course, some of these calculations, they appear very easy when you're working with the real samples. If you work with the complex samples, then it means even the amount of calculations will be much higher. Yeah. So you have got that 10 samples, and this has got 3 samples. So what we do is we just multiply. So if you multiply, since we have 1, 1, 1, it becomes easier, just replicating the same. Yeah, because all this times 1 will give you this, all this times 1 will give you this, and all this times 1 will give you this. It is easy because just a matter of repeating the same sequence. So it becomes easier when you're working with. That's why I chose 1, 1, 1. So let's see what you get. The sequence you're going to get, of course, is the first sample is 1. The second sample is 1, minus 1, 1 plus minus 1, 0. That sample is 1 minus 1 plus 0. That becomes 0. That sample is 1 plus 0 minus 1, another 0. And this sample is 1 plus 1, 2. This sample is 3. This sample is 2. There's something going right somewhere, is it? Or did I make a mistake somewhere? This is 1 minus 1, 1 minus 1, 2, 3. Oh, this is 2. Yeah, then 2 again. 2 again. Then that's 2. Then this is 2. Then this is 3. Then this is 4. And this is 3. Then this is 1. So this is 2. Then again 2. Then 3. Then 4. Then 3. Then 1. So these samples are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so these are samples. I don't know why it looks like it's different from what you had worked out, because I think they are really following one another unless we make a mistake in the other one. Yeah, we must have made a mistake. I don't know which is which. Whether is this method that is 1, 3, 4. This is 3. Yeah, I think we must have made some mistake somewhere, because it's not coinciding. Up here is okay. 4. Is it? Where are we getting? 1, 2, 4. I used the wrong sample. Sorry. I think that's why we have a problem. When I was writing the samples, I made a mistake. I think the sequence is not that one. The sequence is a bit different. My sequence has only 1, 2. Let's see what sequence we have here. The original sequence. The original sequence is here. Yeah. I think this is the 2 I left. 1 minus 1, 0, 1, 1, 2. 0, 1, 2, 1. 0, 1, 1, 2. 0, 0, 1, 2. 1, 1, 2, 1. 0. I'm trying to remember from here. My memory is short by the time okay, 1 minus 1, 0, 1, 1, 2, 0, 1, 2, 1. 1, 0, 1, 1, 2, 0, 1, 2, 1. This was the problem. This is 2. So you need to put 2 everywhere here. Yeah, I think that's where we are going wrong. So this is 2, then this is 4, then this is 3, then this is 3, then this is 3, 4, 3, 1. Yeah, we are good. I think this gives us the answer we got with overlap save method. Yeah, that's what we have. It gives us the 12 samples. L plus n minus 1. So L is 10 plus n is 3 minus 1 gives us 12. So is everybody with the overlap? Sorry, I didn't go to say overlap add method. I think I use the same sequence for overlap save. So the solution for overlap, that's what we got with overlap add method. Yeah. So is everybody okay with the overlap add method? So I hope everybody is okay. So let's look at the overlap save. Very similar to the other one, except that the algorithm is changed slightly. So we are having n-1 samples. We put n-1 samples of the previous sequence. I mean, once you do the division of the previous sequence, we put it as part of your news of this other next sequence. I think let's go to the example, then we don't have to explain that much. So I'm using the same sequence. Yeah. Just to demonstrate, I will use the same sequence. Here it is. Same sequence with the same HN. So we have that. And so what we are going to do is, when we are creating each of these sequences, we have decided to divide into the same length as the h of n. And so we are going to have that and that, and then we are going to pad this one with 2 zeros. Yeah. So that we have 3 samples. So once we do that, so x1n, of course, we don't have any previous samples. So for x1n, we are going to start with, we're going to pad with n-1 zeros. So m is 3, because m is the length of hn. So m is 3, so n-1 is 0, 0. Then that is this sequence. Now, the next one, we are going to pick 1 minus 1, which is the first, the last 2 samples of the previous sequence. Yeah, somebody is giving me the class. Let's see. Yeah. So we are going to add, we are going to start with the last 2 samples of the previous sequence. Yeah. So the previous sequence is this one, so we are going to use -1 0. So we use -1 0 here, and then we put the sequence 1 1 2. Then we take 1 2 here, and then add 0 1 2. The next one, we take 1 2 here, and then add 1 0 0. This is the padded sequence. So we have got x1n, x1 of n to x4 of n. So here we use the same circular convolution method. Yeah, same circular convolution method. If you work out, is going to, you're going to get the y-n's, and how you get your final yn, I mean the yn from this y1 to y4, y1n to y4n, is simply discarding the first 2 samples of every sequence. So it means you discard these samples, you discard this, you are discarding, you discard these samples, you discard these samples. So your final samples will be 1 0 0 0 2 4 3 3 3 4 3 1. So using the overlap save method, we got the same solution. So those are the 2 overlap methods we use, overlap save and overlap add, which is considered to be, it's considered to be a fast uh, convolution method because it is actually faster. It's based on the same. It's based on the same concept as we are going to see with the, let's say, the DIT FFT, decimation in time FFT, because that's the case we are going to look at. That specific one, DIT FFT. There are very many FFTs, but it works on the same concept. Instead of using um, a higher value DFT, you are dividing it into smaller DFTs and doing now and then summing them up. Yeah. And we are going to show that when you do that, especially for complex samples, there's a lot of saving in the number of calculations you do. If you work directly with a big, with a long samples, you actually do more work than if you work with shorter ones and then just do some arithmetic additions. Yeah, because that's what we are doing. We are simply getting shorter samples through this method, and then we are simply adding them up. And we are saying, computation-wise, that is actually better than if you try to work with the entire length. Not to mention, of course, there is the issue of when you use lengthy sequences. For example, if you are doing convolution, and then you use a method like the DFT, and then you use the DFT of such a long sample, is not even practical, because it means, first of all, to even do the calculation, you need to get all the samples. Maybe you're getting 10,000 samples. You have to get your 10,000 samples. Yeah. Sounds big, but it's not big. Because remember, this you're sampling probably at a very high rate. Yeah. Depending on the signal you are dealing with. If you're dealing with voice, then you're sampling at 8,000 samples per second. So when I talk of 10,000 samples, I'm just talking about what you sample in a second. Just about what you sample in a second. So 10,000 samples is not much. So if you're using 1024 DFT, it's better than trying to use 10,000 samples DFT. And that's what basically it means. Yeah. It is going to save you in computation, but it also save you in the hardware. Yeah. Because if you have to, first of all, get the 10,000 samples, you need more memory. You need more bigger buffers. Yeah. Because you are getting the samples and then you must store them somewhere, then begin doing your computation. So practically, it makes a lot of sense to use shorter samples and then add them. That's why we call this one also an FFT method. But we are going to see, just to show with the radix 2 FFT, that actually it is faster to take the smaller value DFTs. That's why we call it an FFT method. They're using smaller value DFT to work out a much bigger DFT. I mean, it's better than trying to work out a much bigger DFT from just a computational point of view. And of course, not to mention that, as I said, the kind of hardware you require when you do when you deal with it, when you try to do DFT of a big number. Yeah. So is everybody okay with these methods of the overlap save and overlap add? Because if we
Excuse me, sir.
yes.
I think the overlap save convolution method wasn't that clear to me. Could you just take a minute and go through the same example kindly?
Or over the confirmation using tabular.
The overlap save method, how to come up with the matrix itself.
Oh, how to come up with the algorithm, the actual algorithm. Yeah. Yeah. So yeah, because counter checking, we just counter checked with the tabular method to see that we get that. And that we get with both overlap save and overlap add. But I think what you want to see is the algorithm for overlap save, isn't it? Yeah.
Yes,
Or
yes.
yes. So what we are saying is you are simply dividing, using just dividing into shorter sequences of length m, where m is the length of the impulse response of the shorter sequence. Yeah, which usually is the impulse response, because the whole idea of convolution is to find out the output of an LTI system when you know the impulse response and you have a sequence. Yeah. So we are saying the method involves is just an algorithm. You get the first, you get the last two samples of the previous sequence, and then now you add the new sequence. Yeah, so the first sequence will be the length of the sequence, but first of all, you get the two of the previous samples. But since this is the first one, so for the first one, there are no previous samples. So what means in that part, in the instead of that, you're going to use 0, 0. Yeah, as just the m minus 1 zeros. Yeah, because m minus 1, but the last two samples, the last m minus 1 samples. So for the first one, there are no samples, there is no previous sequence, because this is the first one, so you use 0, 0. But for the second one, you see, this part is this one, is this part. Yeah, yeah. So you add the last m minus 1 samples of the previous, call it a subsequence. Once you have divided your long block into smaller sequences. So you get the two previous samples, which is minus 1, 0, which is here. Then the next one is this one. And what we are doing, we are simply getting the last m minus 1 samples and putting them here to make this sequence. And the other one, now, of course, this was 1. So whenever you have this, you must make the sequence the same length. So you do padding. Padding is a very common thing when you're dealing with DFT. Yeah? Because with the DFT, especially if you're going to do circular convolution, you need to have sequences of certain length. Yeah? So that is 100, which is this one here, and then we are getting the last two samples and putting them here of this sequence of this. Last two samples are these. Last samples for this one are these. Last two samples for this one are these. So what you're getting is from here to here. Then you get from here to here, and then you get from the next one from here to here. So those are your 4 sequences. Yeah. Now, once we get that, those sequences, which are these ones now, these are the sequences, you simply do use a circular convolution method, which means you're simply getting this sequence, and then You know how we do the circular convolution? You play around with one of the sequences. Here we just play around with the same sequence. Yeah. You could also have done that with this and then multiply with this, but then you'll be making your circular this matrix will keep on varying. So it is easier to that this matrix you make it out of the impulse response to make sense. But even if you worked out with making the matrix from this and then multiplying with the impulse response, you still get the same answer. But it makes out of sense to use the same matrix, even in real sense, because you only store this in memory, and when you get this, just multiply. Yeah. Even operation from the equipment point of view, you are storing only this. But if you did it the other one, it means every time you have to compute this matrix and then multiply with the impulse response. Yeah. So computationally it makes a lot of sense. So you do that, and now you get these 4 sequences. The 4 sequences are this, 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 and this. And then you create your YN. So this is the algorithm for creating the YN. Combine the results of Y1N, Y2N, Y3N plus YN, discarding the first N1 samples of each. Yeah. Of each of these sequences. So that's what we are doing. We are discarding the first M minus 1 samples. M is 2, so M minus 1 is, no, M is 3, so M minus 1 is 2. So we discard the first 2 samples of every sequence. And then just concatenate these subsequences to make your final sequence. Which we found, it gives you the same thing as just using the tabular method of linear convolution. And please, when you ask to use the overlap add, please use the overlap add, because I'll tell you, sometimes when people see it in an exam, they avoid using overlap add. They use the tabular method. They give you their answer. It's correct answer, but you get it wrong because you have used the wrong method. Yeah. Did I answer your question?
Yes, you did.
Okay, very good. There seems to be another question. Somebody has put up the hand or something.
Yes, could you please explain the addition of or just illustrate the addition of the results? Or how to add Y1, Y2, and Y3?
Yes, I just repeated that. So you are discarding the first 2 samples of every of these sequences. The outputs of, because actually these are just outputs when you use the shorter sequence. Yeah. So what you're doing, you're just discarding the first samples. So it means what you get, the sequence will be 100, because you have discarded this. Let me just put X to show you discarding. So you're going to get 100 now in the final sequence. Then discard this, so you get 024, so it will be 100, 024. Discard this M minus 1 samples, so you get 333. So now it will become 100, 024, 333. Then discard this, you get 431. And I think that's what we have gotten here. 100, 024, 333, 431. And you notice these are the last 3 samples of every sequence, because we are discarding the first M minus 1 samples. Yeah. So it is the last M samples, because it's generally our sequence, the sequences we, the length of the sequence after breaking down, well, we chopped it into M length. sequences. So the length is m. The last m samples, because we removed the first m minus 1 samples. Did I question?
Yeah.
Oh, there's a question. Yes, please.
The 5x5 matrix, how does it come out? We just
very no, you can create a 5x5 because and minus j and plus j, 1 minus 1, j minus j. If you go to the 8-point DFT matrix, I think it has 1 minus j divided by square root 2. Then it is quite a complex matrix. 5 would even be more complex, but you would work out the same way as the same way you work out the 4-point DFT matrix. But as I said, normally we don't use those kind of numbers matrix, because when we want to use FFT, then you have to deal with the matrices which are powers of 2. Does that make sense? Does it?
Yes.
Okay, very good, very good. So let's see how you get this matrix, this DFT. Yeah, because you can calculate the same way from definition, because from definition, what is DFT? Yeah. In fact, why do we use DFT? We use DFT because DFT enables us to use FFT. Yeah. That's why we use that. And of course, DFT means you are able, because if you use DTFT, first of all, DTFT is a continuous function, which you cannot use in digital communication systems. That's why we use a DFT. Or rather, DFT just means you are doing frequency sampling of DTFT. Yeah, you are doing sampling of the DFT, the continuous DTFT. That's the most important thing to understand. DTFT is continuous, so you can't use it in discrete time systems or digital systems. So we use DTFT by actually sampling in the frequency domain. Whenever you think of sampling, you think of sampling in the time domain, yeah, but we sample in the frequency domain, and we come with a DTFT. So by definition, the DTFT is divided over x of k is equal to, I think this one you have seen before, n is equal to 0 to n minus 1. So you're only dealing with n samples. X of n e to the minus 2 pi k n capital N over n. You can see all you're doing, you're just replacing in the DTFT, you're just replacing, because how is the DFT? The DFT, we know the DFT, which is x. Okay, sometimes you call it to the j omega, x to the omega, x to the e to the j omega. It is just the same thing. It will be equal to negative n is equal to negative infinity to infinity x of n e times e to the minus j omega n. Yeah, actually that is dtft. Yeah, and this is this is a continuous. Yeah, it moves you from the discrete domain to the continuous domain. Yeah, so we get that. So what you are doing is sampling it. Yeah? So we sample this I to k. Yeah, I mean we are sampling it 8 times. I mean, if it is, for example, if n is equal to 8, it means you're sampling it 8 times. And then, so for each of them will be k is equal to 1, and then k is equal to 2, k is equal to 3. So that is, by definition, that is what is x of k. I think we know that. So if you are going to do direct computation of x of k, this is what we will do. If, for example, if you've got this sequence 1 0 1 1, again we like using just real samples where we are not giving 1 plus j something, is they're just real. So 1 0, and also I'm using 1 0 1 1 to make life easy. And let's consider n is equal to 4. You have decided to sample 2 pi 4 times. Yeah, that is 2 pi f 4 times. So what you're doing is you get, so for n is equal to 4, so these are the n, the small n moves from, I mean the domain of the small n is 0 1 2 3, and k is also 0 1 2 3, because it is 0 to n minus 1. Yeah, if n is equal to 4, it moves from 0 to n minus 1. So x of k is equal to 0 to 3. Yeah, because now we know what is n. That is 0 to n minus 1, x of n, and now we know n, so it is 4. And then we start calculating. So what we want to look for is x of k. So for k is equal to 0, this becomes x of 0 into, so what is now varying is n is moving, this x of k is fixed at 0. So n is moving from 0 to 3. Yeah, that's what this means. And if you work that for this case, it is straightforward, isn't it? For this case, it's straightforward because of this k is equal to 0. Everything, this is actually x of n, because it will be x of n, anything to the power of 0 is 1. So it's simply x of n is equal to x of n moving from 0 to 3. So it will be x of 0 plus x of 1 plus x of 2 plus x of 3. So it will simply be x of n. It will simply be the sequence itself. Yeah, x of n. Yeah. So we go to, maybe I assume you have gone through this before, but still let's go do it again. So it makes it easy to understand even the FFT. For k is equal to 1, because our interest is x of k. K is equal to 1, it simply means you have replaced k with 1. So remember, this was supposed to be 2 pi small k, small n, capital N, I mean over capital N. So because the 2, I mean, if you have 2 over 4, that's why you are just making it over 2. So, and pi, and k is equal to 1. So this k is equal to just 1. So this is n. So this is what x of 1 becomes. Yeah? X of 1 becomes that. So which means it is just x of 0 e to the, so for 0 you have e to the 0, n is equal to 0. For n is equal to 1, it's x of 1 e, now n is 1, so it is simply j pi over 2. X, when x is equal to, when n is equal to 2, small n is equal to 2, so this is x of 2 e to the, now n is 2, so 2 and 2 cancel, so it becomes e to the minus j pi plus x of 3 e to the, oh, I'm losing minus, there must be minus somewhere here. Sorry for that. There must be minus. E to the minus j3 pi over 2. Yeah. And of course that works to that. And now if you work this out, yeah, you can see now you have to convert. You have to use Euler's formula. If you use Euler's formula, that is equal to that. So you want to work with this you're familiar with. This sign of this is easier to work with. So you end up getting that equal to j. So you can see x of 1 is equal to j. Yeah. We have seen that x of me is simply adding the sequence themselves. Yeah. Which of course is 3. That will be 3, isn't it? So mean this is 3 if you're adding x of n. X is equal to 2. Again, we work it out, and x of, it's just going to become 1. Yeah. X is equal to 3. It becomes, what does it become? It becomes minus j. So our x of k is that. So that is working directly. That is called direct computation of EFT. Yeah. But we are saying we can find out that by creating the endpoint DFT matrix. It makes our life easier. And how do you create that DFT matrix? Oh, does anybody have out any problem with what we did, the direct computation of DFT? Does anybody have problem with that?
I have a question.
Yeah.
How does the 3 come about?
The 3. Oh,
yes.
Because we are adding, you see, we are summing x of n from 0 to 3. Basically, what it means, you are adding 1 plus 0 plus 1 plus 1. Because you are summing 0 to 3 x of n. So you're adding, when x is equal to, when n is equal to 1, I mean 0 is 1. Then plus, that's what it means, this summation, you know. This summation is what it means. You get it, eh?
Yes, I do.
Yeah, so that's how you get 3. Any other question? If there are no other questions, let's just see how you get. Without going into details, we have 6 minutes. I'm thinking you don't have to do this again. You can go and work it on your own. But let's just start it. It will save us time if you have not done it before. So x of k is equal to that. So simply because e to the pi, the variables are k and n. But capital N doesn't change, 2 doesn't change, pi doesn't change, minus j doesn't change, and neither does e. So it means this is a constant. And this constant is what we are calling Wn. So this Wn, which is we call it the Twiddle factor. Wn is the Twiddle factor. So once you are able to work Wn, then it becomes very easy to just be raising it. And this Wn for a particular for a particular length of samples does not change. It remains the same. Yeah, because that's the only n. So this is so what we do is just work out that. So what we are saying is for this n is equal to 4, for example, this will simply be x of k is equal to x of 0 w4 to kn. So when n is equal to 0, this simply becomes 0k. General. Actually, this is a general. So generally, that's what you are saying. Yeah. X of k, whatever k is simply that. So you can do for k from 0 to 4. So when you have x of k, it means that is x of 0, this pseudo factor, that's the pseudo factor for n is equal to 4, you write it w4, to the power 0k, then x of 1 to the power n is equal to 1, which is just k, 1 times k, then x of 2, 2 times k, because this is just nk, and this 3 is simply 3k. So from this, you can be able to work out for k is equal to 0, it will give you this. Yeah? Because it goes from x0, x1, and then the pseudo factor. For the first, k is equal to 0. Because k is equal to 0, so this will just be 1. Actually, this will just be 1. Anything to the power of 0 is 1. Yeah. And this is going to be x to the 0. So all these will be 1s because of the power of 0, even this to the power of 0. Yeah, this to the power of 0. Yes. Whenever you have, because this to the power of, if n, any of them is 0, whether it is n or k, that becomes 0. Because it is 2 to the power of kn. So that becomes 0. So that, if you look at it, we have worked that out. I think I've just repeated the same thing. I'm just repeating, this is just the same thing. But that is what we are saying. You can write it in this matrix form. So this form, that's what we are doing. If you have got the x of k's here, if you have got the x of k's is equal to this, you can simply write it in matrix form as this. Yeah, because we know x of 0 is w4 of 0, x of 0, w4 of 0, x of 1, w4 of 0, x of 2, w4 of 0, x of 3. And x of 1 is equal to w4 of 0, x of 0, w4 of 1, x of 1, w4 of 2, x of 2, w4 of 3, x of 3. This is just representing this. So to find, so this is what we call this is a matrix we need to work out. What are these? When n is equal to 4, what are these? And that's what we have worked out, and we have seen w4 of 0. All this is 1, so this is 1. Because of the power of 0, this is 1. So we know this is 1, 1, 1, 1, 1, 1, 1. So what we need to work out is just this. Yeah? So w4 of 1, what is that? It's simply minus j. If you simply use the Euler's formula, that's minus j. W4 of 3, the next one, because we are through with that one. W4 of 1. We have W4 of 2. W4 of 2 is here. W4 of 2 is minus 1. W4 of 1 is minus j, W4 of 2 is minus 1. We have gotten that one. Now we need W4 of 3. W4 of 3 is this one. And it becomes to, what is it becoming? Oh, it's continuing here. Plus j is plus j. W4 of 4, because we are finished with W4 of 3. Now we need W4 of 4. W4 of 4 is what? W4 of 4 is plus 1. W4 of 6 is what we need next. W4 of 6 is minus 1. And W4 of 9 is 1. Hey, we got 1, eh? Or minus, no, it's minus j, sorry. W4 of 9 is minus j. Yeah. It's minus j because it's minus j times 1. It's minus j. That's what you have there. That's it. That's why you have 1, 1, 1, 1, 1, 1. And the ones we have just worked out are these, which is minus j. And it's normally very easy to remember it because what you have is 1, 1, 1, 1, 1, 1, 1. Then in the center here, you have 1 here. Then you have around it minus 1, minus 1, minus 1, minus 1. You see how easy it is to remember? Oh, sorry. The minus 1 should be here. Minus 1, minus 1. Then this is minus j, and the opposite one is minus j, and then this is j, and the opposite one is j. And that is what we call the 4-point DFT matrix. And the 4-point IDFT matrix, the inverse, is simply just a quarter, 1 over n, into this matrix. It is almost the same matrix, except now this becomes plus j, and this becomes minus j. This is now for the 4-point IDFT matrix. Does anybody have a problem with how we derived that 4-point DFT matrix? And you can derive it for any n. Is that okay? Yeah, now tomorrow is holiday, so I don't know whether you are going to have classes tomorrow. We won't have classes tomorrow because it's holiday. For me, I will not have a problem having the classes, but I would not like to force people to have a class during holiday. They may be wanting to go to the stadium. So we need to look for time to, because now the double lessons we have missed 4. The first week, the 2 weeks of strike, and now we are missing tomorrow. And as I said before, this unit is a bit long. Yeah, it's a bit long. We have too many things we have to cover, so we may have to look for time every week to do the double lesson. Not to mention that even the single lesson, we have missed 3 so far. By the end of the week, we have missed 3 single lessons and 4 double lessons. That's a lot. We cannot be able to finish the syllabus unless we look for time to do that. So I think I'll discuss with your class rep, and we agree when we can get that time. We can make it online classes to make it easier. If it is okay with you, it can be very early in the morning or late in the evening. If you are if you are swapped by your program. So so I think we can communicate that. So are there any questions? If there are no questions, please put your